Hi, my name's Ben and this is Nick, and we are from the Centre for Organic Electronics at the University of Newcastle. And today in this video we're going to talk to you a little bit how you would test and characterise a solar cell. This is part of the HSC Depth Study program from the Centre, looking at organic solar cells. You've already received some other material on how the solar cells work, how we manufacture them using roll-to-roll printing techniques. So this video is really about once you've done all that work and created your solar cell, how do we test it? How do we decide what its performance is? So Nick, tell me, what measurement do we use to determine whether or not a solar cell is working well?
Yeah, you might have heard this term before. It's called efficiency, and that's the number that we talk about a lot when we're talking about solar cells.
Sure. Okay. So efficiency, what does it mean? What are we talking about?
Yeah, sure. So efficiency is basically a ratio. So if we were to look at an equation, it might look something like this. Efficiency equals energy out of our device divided by the energy into the device.
Okay. So it's really just talking about how well we're capturing the energy that's coming in, because the solar cells we're talking about today, the printed solar cells, they work the same way as any other solar cell. They're capturing sunlight and they're converting it into electricity. So they're a conversion tool. So this equation is really talking about how well do we capture the energy in, and how much energy are we getting out? So that's the efficiency that we're talking about.
Yep.
So in a perfect world, in a world that doesn't that defies all the laws of physics, we could have all the energy from the sun being captured and being converted into an output, and then we would have an efficiency of 1.
That's right.
Yeah.
Yep.
Okay. So this is talking about energy. We don't normally work in energy as solar cell researchers. We normally work in power, don't we?
Yeah, it's a little bit easier with the tools that we have at our disposal to talk about power. So let's look a little bit more at this energy in and how it relates to power. So the power into our device would be related to our energy into the device over time. And the energy into our device is also defined by how large our solar cell is.
Right, so the area that it's covering. So if I have a bigger solar cell, I'm obviously going to capture more sunlight than if I had a smaller one.
Yeah, that's right.
Okay.
And so to capture those area effects and still keep talking in terms of power, we might instead talk about the intensity of the sun coming in and multiply that by the area of the solar cell.
Right. So this intensity number, that's talking about how much power the light has when it hits the solar cell.
Yep.
And I think the number that we typically use for that is about 1,000 watts per meter squared.
Yeah.
Yeah. So that's an average number. So if you went to some places in the world, it'd be a little higher.
Yep.
And other places it'd be a little lower. So we use that number as a convenient average. And that is, if you were to draw a 1 meter by 1 meter square on the ground, every second you have 1,000 watts of power landing in that square. So this gives us some information about the power in. What about the power out, or the energy out as it is up here at the moment?
Yeah. So if we want to look at that, we need to start looking at what sort of voltages and currents we have produced by our solar cell. So the power out, in this case, would be a combination of 3 factors. So the first factor is how much voltage do we get when the solar cell is disconnected, or as we might refer to it, at open circuit.
Okay, so there's nothing connected. It's just sitting there on its own,
Yep.
and then we can measure that with a voltmeter, and then that will give us a value, and that's what that VOC is.
Yep, and that's the first term.
Yeah.
The next interesting thing to know is what is the current if the device is connected by the positive and negative terminal and we call that short circuit.
Right, so that's where I've taken my solar cell and I've got a big wire and I've connected one terminal to the other terminal. Don't do this, this would be a bad idea.
Yeah.
And we've just joined it together.
Yeah.
So it's all the current that's flowing through that wire, where we're able to measure that with an ammeter.
Yes.
Yeah, okay.
And our third factor, which we might need a graph to talk about, is this thing called a fill factor. And that's kind of looking at the ratio between an ideal solar cell and the solar cell that we've got in front of us.
So this fill factor term, Nick, can you explain a little bit about that? Does that must have an equation as well, does it?
Yeah, it does. So our fill factor is looking at a ratio. So let's look at what that ratio actually is. So this power output that we're talking about here is what happens when we are getting the most energy that we can out of our solar cell. So there's some voltage where we're getting the maximum power out of our solar cell. And then there is some current where we get the maximum power out of this solar cell.
Okay.
And the product of those two is actually smaller than the open circuit voltage times the short circuit current.
Right.
So the fill factor is looking at the ratio between how much power I'm getting at the maximum power
Sure.
of this solar cell and how much power could I theoretically get out of the device.
Right. So this is in a perfect world where, again, we're ignoring the laws of physics. We could get this amount of power out of the solar cell. So that's as you said, theoretical. But this is what we're really getting. This is the real world where we live.
Yep.
And that's what we're getting. So it's the ratio between those two. And I'm assuming that the closer this is to this, the better the performance of the solar cell.
Yeah, ideally a solar cell would have a fill factor of 1, but more realistically we're somewhere in the 0.25 to 0.5 or 0.6 type range.
Right. So that's for these printed solar cells that we're making. So other types of solar cells, so silicon-based ones, they probably have a different fill factor.
Yeah, they could be up around 80 or 90% even.
Yeah. Okay. All right. So we've got some equations now for power in and power out. How do we get an efficiency out of this?
Yeah, so we go right back to the top now, and instead of talking in energy now, we can instead talk about this efficiency being a comparison of power. So we go power out over power in. Okay?
Okay.
And we've got all of the equations now to fill this in. So the power out is the maximum power that we can get out from the device, which is given by this equation here. So we've got VOC times ISC times fill factor. That's the maximum power that we can get out from that device. And the incident power that we have going into that device from the sun is given by our solar intensity and the area of the solar cell that we are testing.
Right. Okay. So with this equation, we're able to get an efficiency for the solar cell, which gives us some indication of how well it's working, which then, if this was measured under the correct conditions, we could then use that number to compare it to other solar cells from other places. Is that true?
Solar cells are being made all over the world. And so this efficiency gives us the first talking point to discuss our results with other scientists around the world.
Okay, great. I think I understand all this, but it might be good now to look at an IV curve, which is the data that we collect to be able to get all these values to put into these equations, and it's also the data that you will be given as part of this program. So we might switch over now to have a look at an IV curve.